We're going to solve this problem to find the eigenvalues and eigenvectors of the matrix. We'll set the problem up using our conventional format, taking lambda off each of the diagonal terms. And we'll set that determinant equal to 0. When we expand this out, we'll take the first diagonal and we get minus lambda times 1 minus lambda squared. Then we get minus 1 times 0, that's nothing. 0 times, that's nothing. And then we have the diagonals in the opposite direction, which give us 0 times minus lambda times 0, that's nothing. Then we have minus 1 times 1 minus lambda. That gives us 1 minus lambda. And then we take 1 minus lambda times minus 1 times minus 1. So we actually have another term that is equal to 1 minus lambda. So we set that equal to 0. When we expand this out, we get minus lambda times 1 minus 2 lambda plus lambda squared, and then we subtract 2, and then we have plus 2 lambda, and we set that equal to 0. Expanding this further, we get minus lambda plus 2 lambda squared minus lambda cubed minus 2 plus 2 lambda, and set that equal to 0. When we bring together common terms, we get the cubic polynomial minus lambda cubed plus 2 lambda squared. Then we have plus 2 minus 1 lambda, so that's plus lambda. Then we get minus 2 equals 0. And we need to find some roots here. And there's nothing that's really obvious, but as I've described previously, I would try guessing roots like 0, which it's not because we have a non-zero constant, then 1, then minus 1, then 2, then minus 2. So let's try 1 and see if that's a root. We get minus 1 plus 2 plus 1. So we have 3 minus 1 so far, which is 2 minus 2 equals 0. So 1 is a root, which means that we can find the other 2 more simply after we complete the division of lambda minus 1, and then we'll put our cubic inside the So what do we need to multiply lambda by to get minus lambda cubed minus lambda squared? We say the top row minus the second one, we end up with lambda squared plus lambda minus 2. Then, with that, we have to calculate what is it we need to multiply lambda by in order to get lambda squared. Our next term is plus lambda. So when we multiply that out, we get lambda squared minus lambda. The first row minus the second row gives us 2 lambda minus 2. So with that, what do we need to multiply lambda by to get 2 lambda plus 2, and we get 2 lambda minus 2, 0. So we've figured it out. We can factor our cubic into this, which I have an easier time dealing with if we multiply both sides by minus 1 to get lambda minus 1, lambda squared minus lambda minus 2 equals 0. What is it we need to multiply? what is it we need to, what two numbers when we multiply them together give us minus 2, but when we add them together we get minus 1. Minus 2 plus 1, when you multiply those together you get minus 2, but when you add them together you get minus 1. So lambda minus 1, lambda minus 2, lambda plus 1, and all that's equal to 0. So our roots are, so the eigenvalues are minus 1, 1, and 2. Now we just need to find the eigenvectors associated with each of those. And we'll start with 2. So for lambda equals 2, let's find the eigenvector associated with that. So we set up the system of equations where we take 2 off each of the diagonal terms. The first entry in the matrix is 1 minus 2. 1 minus 2. The next component is minus 1, then 0 and 0. Then we have 0 minus 2, minus 1, 0. And last row is 0 minus 1, 1 minus 2. I'll just save myself a bit of time. This first entry is 1 minus 2, or minus 1. So let's perform Gaussian elimination on this and see where it gets us. So in our next step, we would take row 1 minus row 2. So we'll keep row 1 the same. And we'll go forward with our next step. Row 1 minus row 2 is equal to 0. Minus 1 minus a negative 2 is 1. 0 minus a negative 1 is 1. And then we have our last row. And if you advance Gaussian elimination, clearly we're going to be able to get rid of row 3 just by, it's clearly, row 3 is clearly a multiple of row 2, so that's our final result. That's our final result from Gaussian elimination. And what equation 2 says is that x2 plus x3 is equal to 0, or x2 is equal to the minus x3. And from equation 1 we get that minus x1 minus x2 is equal to 0, or x1 is equal to minus x2, but we know that x2 is equal to minus x3, so x1 is equal to x3, and that tells us that if we choose x3 to be arbitrarily set as 1, then x2 is minus 1, and x1 is 1. So that's the eigenvector for lambda equal to 2. And we have our first eigenvector eigenvalue pair. Now let's continue and we'll find the eigenvector associated with lambda equal to 1. So we'll take 1 off each of the diagonal terms, which gives us the system of equations 0, minus 1, 0, 0. We already know what x2 is. The next one gives us minus 1, 0 minus 1, oops, that last one is 1 minus 1, so we don't actually need to perform any Gaussian elimination. We can tell from inspection here that the first equation and the third equation tell us that minus x2 is equal to 0, or x2 must be equal to 0. Now that we know that, then we can use equation 2 and say minus x1 doing very well. Minus x1 minus x2 minus x3 is equal to 0. And because we know that x2 is equal to 0, that falls out, and we can say that x1 is equal to minus x3. Or, if we choose x3 to be 1, then x1 is 0 and x2 is 0, and that's the eigenvector for lambda equal to 1. We only have one last eigenvector to find, and that's for lambda equal to minus 1. For lambda equal to minus 1, we subtract a minus 1 from each of the diagonal terms, or basically add 1 to each of the diagonal terms, and we get 1 plus 1, 2, minus 1, 0. Next row we get minus 1, 1, minus 1. Then we get 0, minus 1, 2. Oops. I forgot about my column of zeros. And when I go forward with Gaussian elimination in my next step, I would keep row 1 the same. And in row 2, I'm going to take 1/2 of row 1 and add it to row 2. So 1/2 of row 1 gives us minus 1/2 plus 1 gives us 3/2. Minus 1/2 times 0 plus 1 minus 1 is minus 1. And set that. I did this wrong. If you go back and look at what I just did, I screwed up on this term right here. Again, my task here was to take 1/2 of row 1 and add it to row 2. So I should have had minus 1/2 plus 1, or 1/2. That's supposed to be a 1. So 1/2 is a component. And then if we just copy row 3 over again, we discover that row 3 is really just a multiple of row 2, so that in the next step we just have row 1 copied over, and you could just take 2 times this row 2 and add it to this row 3, and you'll see that if you take, again, 2 times this row 2 and plus this row 3, you get 0, 0, 0, 0. So from this we can say, from that equation we get 1/2 of x2 minus x3 is equal to 0, or x2 is equal to 2 times x3. From equation 1, we know that 2 times x1 minus x2 is equal to 0, or x1 is equal to 1/2 of x2, but we know that x2 is equal to 2x3, or so we could also say that that's equal to x3, which means that if I choose x3 equal to 1, then I get an eigenvector that looks like that, and that's the eigenvector for lambda equal to minus 1. And so now I found all 3 eigenvectors and eigenvalues.